Okay, so let's get started. So this class, we're going to discuss a new topic on aerosol measurement. That's the aerosol hygroscopicity. So let's do a quick recap of our last class. So last class, we mainly talked about aerosol generation and calibration. We introduced different aerosol generators that include the nebulizer or atomizer, the electrospray, the vibrating orifice aerosol generator, fluidized bed generator, and aerosol reactors that's going through these high temperature and then nucleation, coagulation, condensation processes. And further, we can use these aerosol generation methods and then to provide aerosols for the calibration of the instruments. For example, we said that we could use the PSL particles that has very precise control of the particle size, and then use them to calibrate let's say the DMA or other, let's say CPC or other instruments in terms of to characterize their size dependent performance. And we could also use the differential mobility analyzer, the DMA, to classify particles of specific sizes and then introduce them into different instruments, right? So this class, we're going to talk about the aerosol hygroscopicity, which is a quite specific measurement. We talk about the mass measurement, number concentration measurement. So these are different quantities, right? The size distributions. Aerosol hygroscopicity is also one important property that people spend a lot of efforts to characterize. So why do we need it? So here I'm listing a few aspects or a few reasons why we need to do those measurements. First, the aerosol hygroscopicity affects the visibility. Remember, in our first class, we give these comparisons of the national parks. And we asked the question, like, if you consider the PM 2.5 or PM 10 concentrations, you see that for the Glacier National Park, they actually have lower concentrations of these PM mass concentrations, right? But they look more hazy compared to the Yosemite National Park. We said one reason, or one very likely reason, is that over the lake, the aerosols just absorb. It's easier for the aerosols to absorb water vapor so that their size just grow to much larger, right? Then they can scatter more light and then reduce the visibility. So this is related to the hygroscopicity of the aerosols, and then which will place an influence onto the visibility of the aerosols. And the aerosol hygroscopicity also affects the people's health, mainly because when we inhale these particles into our lung is also a highly humid environment. The RH can go as high as 99% or even supersaturation conditions. So because of that, we need to understand how the aerosols absorb water, grow in their sizes, and further get deposited into different regions of the human respiratory system. But I would say a more important reason why people are interested in hygroscopicity, or most of the studies measuring aerosol hygroscopicity, is to understand the aerosol cloud interactions. Because these suspended aerosols, once they get lofted into our, let's say, the higher atmosphere, still within the boundary layer, then we know that the temperature is going to reduce. If the temperature reduces, then the vapor pressure of the water is going to reduce, which will create these near saturation or supersaturation conditions. And once the supersaturation condition is created, then we're going to form cloud droplets. And then they're going to basically form clouds, right? And then they will reflect the solar radiation reaching to the Earth's surface and then further place an influence onto the Earth's climate. So that's why people are interested, or many of the atmospheric scientists are interested in the aerosol cloud climate interactions, and then they need to measure the hygroscopicity of the aerosols. I would say regarding the hygroscopicity of the aerosols, I strongly encourage you to read this paper because this is I would say a canonical paper that summarizes the aerosol hygroscopicity with just one single parameter. So reducing all of these analyses into one single parameter is very helpful for the building up sophisticated models to look at the aerosol cloud and climate interactions, especially in the global climate models, right? So we know that the climate model is mainly covering, let's say, the land surface, the ocean surface. We need to consider the temperature, wind speed, wind direction, all of those parameters. So we don't want to overcomplicate the aerosol model. So by reducing the aerosol cloud interaction into this one single parameter model, that is the hygroscopicity, or people call the kappa value, it really simplifies the computation power, computation need for these climate models. Okay, so we'll just briefly go over how we measure the hygroscopicity of the aerosols, but I think it's necessary that you read this paper to understand more, like regarding the equation derivation and how do we, let's say, how do we verify these theories and then further apply these theories for aerosol hygroscopicity analysis. Okay, so what is aerosol hygroscopicity? Aerosol hygroscopicity is the tendency to uptake water, right? So, for example, here it's giving you several different types of salts or different types of chemical species, right? So they can have different initial particle sizes. For example, let's assume it's 100 nanometers. Then, if you expose these aerosols under certain relative humidity, their size is going to change, right? For example, for the ammonium sulfate, if you place this 100 nanometer ammonium sulfate particles in the air, right? If the RHs remain constant, then their size here on the y-axis is showing you the size ratio, which is the grown particle size divided by the initial particle size, T0. Right? You can see over the large range of RH until around 80%, the size really didn't change much, right? It's still the original size. But until a certain point, right, the size rapidly grow into another, like larger size. It has a growth factor of around 1.4, which means that the particle size is going to increase by around 40%. This is what's showing here. So if you have a solid particle that's crystallized, right, here we're showing the pure substance, right, has certain crystallinity. And then when you expose it to high RH, then it will suddenly absorb water under certain RH and then grow into a liquid particle, basically a droplet. We call this transition point as the effluent, as the deliquescence point. The deliquescence point is basically where the aerosol is going to absorb water rapidly and then grow into a droplet. So if you may imagine, well, we could also reduce the RH from these higher ends, right? So the RH can continuously decrease. But now when it comes back, it's not going to follow this deliquescence point. It's actually going to reduce the size gradually, shrink droplet size more and more until at a certain point it crystallizes again and then form solid particles. So that is called the efflorescence process, where this transition point is called the efflorescence point, right? So this deliquescence point, efflorescence point, actually applies to many of the chemicals that we face in our daily life. For example, sodium chloride or any of the salt particles will show these. It is actually for the organic particles that don't show these type of feature. And for some of the organic particles, they don't show this feature either. For example, the sulfuric acid, right? You don't really see a deliquescence or efflorescence. For the ammonium bisulfate, right? I think it kind of show a efflorescence point, but doesn't have the deliquescence point. These are quite useful because you can see, because these particles are hygroscopic, right? So under different RH, they're going to have different sizes. And further, if we increase the RH to all the way to above 100%, which is basically the supersaturation, then they can grow into cloud droplets and further make their sizes even larger, right? Another thing I want to point out that this is an equilibrium process, which means that when you set the RH to 90%, then the ammonium sulfate particle size is just going to be around 1.5 of the initial size. It's not going to grow or shrink as long as you fix the particle size to 90%. This is 85%, right? So this is deliquescence or efflorescence. So basically here, the species we show also have, all have these hygroscopicity, which means that they can absorb water vapor. What if there's a particle that doesn't uptake any water? So one example can be metal particles, right? So we can suspend a pure stainless steel particle in the air, right? If they're in the nanometer range. In that situation, it's not going to uptake any water, right? And then it's just going to be a water, let's say a film of water, right? Water liquid surrounding these metal particles. And under this situation, this droplet is just going to behave the same as a pure water droplet, because if you consider the uptake of water or these deliquescence and efflorescence, is basically the surface interaction between the ambient environment or the water vapor in the ambient environment and the droplet surface, right? So for the aerosol that doesn't have any hygroscopicity, right, when basically the kappa value equals 0, which is a parameter describing the hygroscopicity, basically it means that it's not soluble in the water, right? It's just retains a solid form in the water. Okay. So actually, regarding the let's say the water uptake or the hygroscopicity, I think in your aerosol science and technology class, you probably learn about this equation here. So which is basically the log of P, which is the vapor pressure divided by so this is partial pressure divided by the vapor pressure along a flat surface equals these two terms, right? So further, the ratio between these two pressures are the saturation ratio, right? Basically, this is the actual partial pressure divided by the saturation vapor pressure. And this is specifically talking about the saturation ratio over a droplet, right? And we further mention that this first term is related to the Kelvin effect, the second term is related to the salt effect, or the solubility of the particles. And that effect is called the Raoult effect. So we can briefly introduce the Kelvin effect, Raoult effect again. So basically for the Kelvin effect, what it means is that when you have a curved surface or the curved droplet, then the packing density of this liquid or water liquid here is going to be higher compared to a flat surface, which means that it's going to try to push these water vapor into the gas phase. And that's why the vapor pressure that's directly above this curved surface, right, is going to be higher compared to the saturation vapor pressure, because you can see this is always a positive term here, right? No matter what size you have, this is always a positive term here, which means that this partial pressure is going to be higher compared to the vapor pressure along the surface. And also you can see the smaller the particle, the stronger the Kelvin effect, which means that smaller particle, this term gets larger, then you will generate a higher partial pressure along the surface of the droplet, right? This is the Kelvin effect. There's also Raoult effect. So the Raoult effect actually reduces the vapor pressure. You can show that more clearly in this picture here. So when you have Raoult effect, then you basically have some non-volatile solute molecules that are getting dissolved into the liquid, right? So we mentioned the ammonium sulfate, ammonium bisulfate, or sulfuric acid, they're getting dissolved and they're not evaporating into the gas phase. So because of that, you're reducing the concentration of the water molecules in the liquid phase of the droplet, right? Compared to the pure water case. So in this case, you're actually generating a lower water vapor or the water vapor partial pressure along the surface, right? So this is going to give you a reduced or a negative term that reduces the partial pressure that's along the surface, right? So you may also see this term here, right? So how is this equation different from this equation? Actually, in the aerosol cloud interaction studies, people use this equation more. So there's a simple way to convert this, right? So what you can do is basically here, this term is the saturation ratio, right? And then further, this saturation ratio, when the saturation ratio is above 1. Okay, so people can also show this as 1 plus S. Right, so 1 plus S. So in this term, the S term here is just the supersaturation. I'll just use an S as the term here. So it's a supersaturation, right? We also know that if the S is not significantly high, right? If let's say the S is relatively small, then the log of 1 plus S is close to S, right? This is just the Taylor series expansion. So this is how you can get this equation here. And then you have the Kelvin effect and Raoult effect. So we say that this supersaturation or this S term is small, mainly because people use this equation a lot when they are trying to look at the aerosol cloud interactions. And in the clouds, the supersaturation is normally below 1%, right? In very rare situation, it can go above 1 to 1, let's say 1 to 2%. So which means that we can comfortably use this equation and then just use S here, which is the supersaturation, to show the Kelvin effect and the Raoult effect, right? So we have these two effects. How do they show up when we are trying to, let's say, describe the supersaturation as a function of the droplet size, right? How do we show that, let's say, we have the mathematical equation, how do we understand it, let's say, in the real situation? So here we're just talking about the cloud formation. Let's just forget about the, let's say, the low RH or non-saturated condition. Now let's consider the cloud condition, which has some supersaturation. Okay, so basically this Kelvin effect and the Raoult effect are going to counteract against each other, right? The Kelvin effect, if you show that, that's going to be the red curve. The Raoult effect is the blue curve here, and the negative Raoult effect. So if you plus these two terms together, then you are going to have this supersaturation as a function of the droplet diameter. Okay, so this is assuming that the particles have a chemical composition of ammonium sulfate. Just write it out. And then has an initial size of 50 nanometer. So what this means is that if you give it certain supersaturation, okay, of this ammonium sulfate dry particles, then it can grow to a certain droplet diameter. Okay, so for example, if you give it a negative 1%, which is 99% RH, okay, so this will mean that the droplet particle will grow to a size of around, this is 200 nanometer, this is probably 120 nanometers, okay? And then you can further increase RH when it gets to 99.5, then the size is close to, let's say, 150 nanometers, okay? So you can size can further grow when you raise up the supersaturation until, let's say, it rise to around 0.4, 0.45 supersaturation, okay? It reaches to this droplet size. Okay, so what's going to happen next, right? So you see, the next is that basically, in order to let the droplet size grow, you don't need even higher supersaturation. So what this means is that under this supersaturation, the droplet size will continuously grow by itself, right? So they will just keep going and then grow to the eventual sizes, right? Because now you have sufficient amount of water vapor that can grow onto the droplet. And then at the same time, they don't need this high supersaturation, a further high supersaturation to maintain the droplet. So this means that the droplet is just going to automatically grow by itself. And this is why people also call this as a critical supersaturation, right? Where the aerosols will form into the cloud droplets. Okay, but actually for this relationship here, if you remember this paper here, it has a derivation or a more mathematical understanding of this process. And this equation is just decided by this equation here, where the S is the saturation ratio. It's actually not the supersaturation. S is saturation ratio. The D here, this is a droplet size. The DD, this is not droplet size, it's a dry particle size. Okay, or the initial particle size, where the kappa is the hygroscopicity of the particles. Sigma is the surface tension, molecular weight of water, density of water, droplet size, gas constant, and temperature. So basically, this is how to get this equation. So what happens is that you can plug 50 nanometer as the dry particle size. You know the hygroscopicity of the ammonium sulfate, and then you just plot the S as a function of D, right? This is how you get this curve here. So this also shows that if you give it an initial particle size, and if the cloud has a supersaturation of, let's say, higher than 4.5%, then you automatically form the, let's say, form the droplet into, let's say, tens of micrometers. They go to the cloud droplets, okay? So then we mentioned this critical supersaturation. People also call this as the activation barrier height, or the SC, right? So then you can see that this SC is really dependent on a lot of properties, right? It depends on the dry particle size, right? So basically, what you can do is you can just take a derivative of this S over D, right? And set the derivative to be 0. And you can see it's dependent on the droplet size and the hygroscopicity, right? So basically, you see that for different initial sizes, you're going to have different different curves. It's not growth curves, different curves. And for different chemical composition, you're going to have different curves as well. So now we know the mathematical equation describing the aerosol hygroscopicity. So how do we measure the hygroscopicity, right? So we said that the hygroscopicity parameter is one that's most important. So if a particle is more hygroscopic, right, like ammonium sulfate, right, then you can, let's see, which one is more hygroscopic? Sodium chloride. If sodium chloride is more hygroscopic, right? So it can grow into cloud droplets that require lower supersaturation, right? And for the larger particles, they can also grow to the droplet more easily, right? So how do we find out the aerosol hygroscopicity? Okay, so commonly there are two ways to do that. One way is to use the tandem differential mobility analyzer, because remember, for this equation here, remember how many unknowns we have. We have the S as one parameter, I would say unknown, right? D is an unknown, the D is an unknown, and kappa. So you have 4 parameters, right? If you know any of the 3, then you could determine all of them, right? So basically for the TDMA method, what it does is that it first classifies particles of different sizes. It can be dry size, right? The DD in there. And then it goes through a humidifier that you control, maintains certain relative humidity, right? For example, 80% or 90%. You also maintain that in the second DMA. And because of that, the particle size will grow, right? Initially, you'll have this size, and then after that, it's going to grow to another size. So you have the dry size, and then you also have the grown particle size. You also know the RH, right? That's the basically the supersaturation, right? Although the supersaturation is a negative value. So you know all of these 3. So then you can find out kappa, right? That's how simple it is to use the TDMA method. But people argue that, well, for this equation to work, right, you need to make sure that the supersaturation is close to 0, right? So because of that, you don't necessarily can use this equation here to do the Taylor series expansion. So because of that, you also need to do it in a more accurate way, right? So people also find out that the HDDMA method, which measures the kappa value here, it's somewhat different from what people measure in the supersaturation condition. And we're going to talk about how to do the measurement under the supersaturation condition, right? So for the TDMA, this is subsaturation. And then there are also methods that does the supersaturation conditions, does the kappa measurement under supersaturation conditions. Okay, so for the TDMA method, there are several advantages, right? So it has a high size resolution. You just do the DMA size classification, and the second DMA can scan the size distribution. It measures nanometer size range, right? It can measure the hygroscopic growth and derive the kappa value. And then there are also confounding parameters, confounding factors. For example, the shape of the particles will matter, right? So one thing is that in our first class, we mentioned that there can be soot particles that has these branch structures. So one thing people find out is that when you expose these particles into high RH conditions, actually these structures will collapse into a smaller particle, right? So if you consider this situation and then plot the particle size distributions, if let's say this is the initial size, and then after they grow, they actually can grow to smaller sizes. Under this situation, we can't really determine the kappa value, right? And also, this is an ensemble measurement. You don't have the, let's say the size specific or the more detailed information about the hygroscopicity. And further, the measurement speed is quite limited, because just imagine if you need to use a fixed size to by the DMA at specific size, and the second DMA need to scan for the size distribution, which we said that it's going to take some time for each scan, right? And you want to do multiple scans at each specific size for accuracy or counting statistics, and then change the initial size to do more scans. And because of that, it will create some challenges when you're trying to do fast type of measurements, right? So there are methods to do fast measurement. For example, people actually replace the second DMA with an optical counter, right? OPC. OPC can detect the optical size of the particle, optical size distribution of the particles. So you could classify it with the DMA, right? The particle sizes with DMA, and then basically measure the grown particle sizes with the OPC. But we mentioned that the OPC measurement depends on the refractive index, and also it cannot really get to the very small sizes, more sensitive to particles larger than 100 nanometers. So because of that, it's kind of limited when we're trying to look at the hygroscopicity of very small sizes, especially the newly formed particles, right? So another way to do that, this is a method that's been developed by my postdoc advisor, Jian Wang, now at Washington University. So basically, he created an instrument that's called the fast integer mobility spectrometer that measures the particle size distribution at high speed. Okay, so I also introduced this instrument when we talk about the size distribution measurement with the SMPS. So basically, for the FIMS instrument, it can scan the particle size distribution at a speed of, let's say, every 1 second. Right? Basically, it grows the particles based on condensational growth, and at the same before they're grown, you have the mobility separator to separate them based on their electrical mobility or their sizes, and then after they're grown, the location on the image, right? So here is a laser that shines upon them. The camera will take pictures from the below. So the location of these particles on the image will relate to the particle size. That's how you get time resolution measurements. So because of that, you get rid of the second DMA, which scans the size distributions, right? So the first DMA can just select particles, and you can do several seconds of size scan, which shortens the time of the hygroscopicity analysis. Okay, so this is how the FIMS is being used for the hygroscopicity analysis, right? And one thing I also want to mention is that for the FIMS, remember when we first introduced it, it uses the butanol vapor or heptanol vapor to grow the particles. But we also need to make sure that the RH in the humidifier is the same as the RH in the FIMS. So that's why for the H-FIMS, it uses water vapor to grow the particles. Okay, so that's the advantage part for particle growth. So the FIMS can actually shorten the particle size measurement from 300 to 20 seconds, right? So which can significantly reduce the time that's needed for the aerosol hygroscopicity measurement. So these are the measurements for the sub-saturation condition, let's say sub-saturation condition for monitoring the hygroscopicity. There are also instruments that do supersaturation condition, right? So for the supersaturation condition, it is more close to the cloud condition. So people created these CCN counters, or the cloud condensation nuclei counters, right? Which operate at the supersaturation that's just close to the cloud condition. So this is a more, I would say, a more straightforward way, because we want to understand the aerosol cloud interaction, right? So we want to see how many aerosols are forming cloud droplets. Why don't we just create a cloud chamber, right? Create the condition that's in the cloud, and then count how many cloud droplets are there, how many larger droplets are being formed from this instrument, right? So basically in this chamber here, then you are going to create a supersaturation by varying, let's say, the temperature and flow rate in the growth tube, right? To basically create supersaturation with different values. So this is how the instrument looks like. So the instrument is now commercialized by the DMT company. That's the full name is Droplet Measurement Technique, right? So there are equations that determines the supersaturations. As you can imagine, while there's basically the temperature profile being established, the supersaturation being established, one thing we should notice is that the supersaturation is not uniform, right? So that's why the aerosols are being introduced from the center only by using a capillary. So they're exposed to a similar supersaturation. There are equations to determine the supersaturation. So there are theoretical equations. Basically, the supersaturation is just the vapor or the saturation ratio is just the partial pressure divided by the vapor pressure, and then according to the let's say the thermodynamics equation, right? This is basically how the partial pressure is determined, right? So then you can incorporate the temperature profile, the temperature gradient into this picture, and then to find out how the let's say the saturation ratio is dependent on the settings of the instrument. So it's related to the temperature gradient, G, the total flow rate through the instrument, and also this two diffusion terms. So one is a mass diffusivity and the other is a heat diffusivity. But both for these two terms, they're 1 over the terms are proportional to pressure. So the lower the pressure, the higher the diffusivity, right? So because of that, basically this whole term here is proportional to pressure, the gradient, temperature gradient, and the total flow rate. So there are some calculations regarding how the supersaturation is dependent on these parameters. But these are still model measurements, right? Model measurements. How do we know that our growth tube just create this accurate supersaturation conditions? Okay, so to create this condition, we have to make sure that our instrument is being calibrated with the with a known type of aerosol, right? So it needs to be calibrated using aerosols with well understood hygroscopic properties. So what people do is that you can classify aerosols with a DMA, and then basically to send particles of specific sizes, and first to get their total concentration, right? A CN is a cloud nucleus or condensation nucleus, right? The total concentration. And then you can send the rest of them, send the same stream of the aerosols into the CCN counter. So by sending them into the CCN counter and operated under unknown supersaturation, right? Unknown supersaturation, you can also get the NCCN. So you can switch the DMA sizes, right? Change from the smallest size to the largest size. And then you expect that you'll get a curve that looks like this. In the very small sizes, the particles won't get activated. They won't grow into cloud droplets. But at a certain point, all of them get grown into the cloud droplets and then stay, let's say the efficiency will go to 100% for the rest of the sizes. So remember, for that equation, we determined that include kappa, the droplet size, the initial particle size, right? And then the other unknown is the supersaturation, right? So here, supersaturation is unknown, right? Kappa is known because we are using ammonium sulfate, right? Specific chemical composition. The particle size is also known. But one thing is that, you see, the droplet size, we don't know that. But one thing we know is that during this transition, it's actually happening at the location where you have this highest or this critical supersaturation, right? So basically, you know the condition corresponding to the first derivative against the droplet diameter, right? So you know this is the, basically you set the derivative to be 0. And you know what dry particle size is corresponding to that. So basically you have a third boundary condition, right? So you have 3 knowns, and then you have 1 unknown, and then you can solve the saturation vapor pressure, right? So there are some issues associated with these calibrations. We're just going to quickly skip through these. And then people also use the side result CCN measurements, basically to use after you calibrate the instrument to find out what are the actual supersaturation, and then you could do this measurement for ambient aerosols to find out their kappa values, right? Because now if you know the S, right? If you know the S, if you know the dry size, and then you know the critical supersaturation where they're getting activated, right? And then you can find out what's the kappa value, right? So it's the other way around. So you could also use this instrument to determine the aerosol mixing state. For example, the TDMA, you can do that to determine the mixing state, right? It's because particles may grow into different sizes, and then it's because of the mixing state that's different, right? You can also use the SCCN to do these measurements. Okay, so that's it for this class. We're just quickly going through some concepts. And then it's mainly about the aerosol hygroscopicity analysis. That's it. Talk to you next time.